Okay. Uh, Good morning, good afternoon, wherever you are. I'm from UK. Let me set the timer first. We will go for 30 minutes. Okay, that's fine. All right. Welcome to this channel. On our last video on lectures on electromagnetic induction, Lenz's law, and Faraday's law of electromagnetic induction, we discussed few things. We discussed how the induction is done, how change in magnetic, specifically change in magnetic field creates current. All right, and we discussed how the area confined, where we discussed the conditions where there were two conditions, one two loop condition, next is one loop condition, and how two loop condition and one loop condition are different when we study in depth about electromagnetic induction. So we got a detailed review on every of those, and those who have not watched it, please go to the previous video and watch it. So on today's lecture we will be starting something a bit more in depth about magnetic flux, that will just end up with what is basically fundamentally meant by electromagnetic induction, that is Faraday's law. We will, in this class today, we will study in detail about what is essentially what is Faraday's law of electromagnetic induction. All right, so let's start. mm, I'll just start within a minute. Okay. So what do we understand here is, we generally understand that here is a loop, here is next loop. Let me call it this loop number one, let me call this loop number two. So when there is a change in magnetic flux, when there is d phi by dt, d phi by dt, d phi by dt, change in magnetic flux on one, then there is current induced. What is induced? Current is induced, or EMF is induced. EMF is induced on 2. All right, EMF is induced on 2. So when there is change in dB dt in 1, EMF is induced on 2. This is quite non-intuitive. On my previous lecture I have explained why this is so, because the change is confined in a small area. All right, the change does not varies. The change is confined in a small area. It's just like divergence. No matter how much you change the shape, the divergence, which is from the confined space, will always be the same. All right, so this is dB dt due to 1. This is dB dt due to 1. Now, what essentially Faraday says is, no matter it is due to 1, no matter it is due to 1, the change in dB dt due to 1, but the EMF is induced on 2. Okay, the EMF is induced on 2. So what basically happens is, the change in magnetic flux, the change in magnetic field, essentially it is change in magnetic field in 1, it will associate with the change in magnetic flux in 2. Basically it is the same, like change in magnetic flux in 1, but the change in magnetic flux in one is same as the change in magnetic flux in two. For example, I'll just elaborate. For example, here we have something, let's call it q. Okay, and it has a divergence. Okay, it has a divergence. I'll not it has a divergence. So I've already explained this. It has a divergence. The arrow represents divergence. Now, even if I make this outer circle this much or this much, okay, or I just take this like a reference, the frame of reference, the q as a circle, then no matter if I choose this one, this one, two, this one, three, the essentially the divergence is same. It is same. Just for your understanding, just imagine this one is a water. All right, water that is shooting out. No matter if you choose this surface 1 or if you choose this surface 2, okay, or if you choose this surface 3, no matter what surface you choose, the amount of water that comes out is the same, because the amount of water that is confined in this space is the same. So no matter it is dependent on it, okay, it is dependent on it, but this is two loop case. But in one loop case, the loop is anyway associated. Here we are talking about two loop case. No matter it is dependent on the primary loop, what we will understand is the change in flux in primary loop is same as the change in flux in secondary loop. All right, same, because the no matter if I distort this surface, it will the amount of divergence or amount of flux that comes out is the same. The amount of flux that comes out is the same. The flux does not changes. Okay, so the amount of flux that comes out is, so the change in flux in one is the same as change in flux in the two. All right, so this is the basic fundamental concept that you must understand. If you still don't understand, please let me know. I'll explain or I'll make a special video on it. If you just tell me in comments and things. So this is the basic concept of what Faraday told. Why we are dealing with this is because we have a special concept on it. What special concept is? Just see here. Okay, why we are taking this? Okay, let me just. This is one. This is two. Okay, current is induced. I'm just taking the direction arbitrarily. No any confusions. I'm just taking the whichever direction I want, because I haven't specified the other parameters. Now, because now let us discuss the magnetic flux. Now let us discuss the magnetic, I'm sorry, uh, magnetic field change in one. Okay, the magnetic field change in one is same as the magnetic field change in two. Okay, then magnetic flux change in one is same as the magnetic flux change in two. Okay, so what essentially, let's first, I'll make you understand. It's a long process. It's a very important concept. You need to get that concept sink in. Otherwise, it will be beyond your comprehension. Okay, let's discuss what is flux. Okay, what is flux? Essentially, what is flux? Uh, this is a surface. This is an open surface. Let's say a piece of paper, all right, or a handkerchief. Open surface. Okay, and on this open surface, I taken a teeny beeny little area called dA. Let me say this area called dA, and please see this. This area is always always in the direction, in the perpendicular direction to the surface. This area is always perpendicular in the direction to the surface. Okay, to the surface. Surface. Okay, it is always in the perpendicular direction to the surface. Let us just assume that this is how it works. Okay, the dA is perpendicular to the surface, and that's a perpendicular vector. Now let us say, for instance, the magnetic field is in this direction. Okay, magnetic field is in this direction. Okay, then what is then the total amount of magnetic field, then the total amount of magnetic field that comes through this surface, total amount of a magnetic field that comes through this surface, okay, that is basically flux, is defined as, this is phi flux. Let me flux of B, magnetic flux, because we have electric flux also. So magnetic flux is essentially defined. How it is defined is, I'll elaborate it. It is defined as the integral. Okay, it is defined at the open surface integral. Okay, it is defined as the open surface. Okay, it is defined as the open surface integral, because the surface is not closed, it is open surface, it is an open surface. That is why magnetic flux is able to be passed, isn't it? It is not the closed surface, it is open surface. Now magnetic flux is defined by B dot D. So this is essentially what is magnetic field, magnetic flux. This is essentially what is magnetic flux. Now, what essentially Faraday says is, it is the change in this magnetic flux. Okay, please understand. It is the change in this magnetic flux, that and there is a very important concept, that that will induce the current, okay, on the circumference of that open surface. I am drawing the circumference, please see it, on the circumference of that open surface. What is here? Circumference. The surface in which there is change in flux, current is induced on the same circumference of the surface. Okay, for example, here, the surface, this is the surface we are talking about, this is the surface. So on the circumference of that open surface, current is induced. So current is induced, as I have indicated by the red lines. Current is induced here in this loop. Okay, current is induced in this loop. This is very important concept, it needs to sink in. Current is induced in that loop. Current is induced in that loop. Please see this. Current is induced in that loop. This is magnetic flux. Okay, we are connecting to a Faraday's law. Wait, current is induced in that specific loop. All right, so why are we worried about the area loop 1 or loop 2? Because the current is induced in loop 2. That is why we will be associated in the flux change in loop 2. But actually flux is confined on 1, so the flux change on 1 is same as the flux change on 2. actually it is confined on one, so flux change on one is same as the flux change of two, no matter if I increase the size or decrease the size, because I've already explained it here. Because because the divergence, no matter if I create this big or this small, the divergence, the amount that flows out is the same. That is why we are concerned about the second loop. Okay, if there is only one loop case, it's easy. The only loop associated is loop one. But here we are associated with the two loops, so we need to take in account the for the both of the loops. All right, so you got an overall idea of why two loops case, all right, magnetic flux, and why the magnetic flux change through loop 1 is the same as magnetic flux change through loop 2 because of confinement. Okay, you got the basic idea, you got the idea for what is flux. All right, now essentially what Faraday says is, let me just explain you now. Now, essentially, what Faraday says is, Faraday says EMF, EMF. Faraday says EMF induced is equals to minus the minus d phi by dt. Okay. So this is what essentially Faraday says. The EMF induced is directly proportional to the flux change, and we just what the negative sign that is introduced here, the negative sign that is introduced here, it is of no like no significance, because anyway we will be able to find out which direction it is just there to comprehend, to associate Lenz law. Even if you ignore the minus sign, you will know which direction the current is going, but just to be mathematically correct, it is kept there. Just to be mathematically correct, it is kept there. All right, now this is the small amount. This is not Faraday's law, please see this. This is just a small amount of a Faraday's law. Okay, you might have studied this is Faraday's law, but this is just a small amount of Faraday's law, because Faraday's law just says, what does it says is, it says the change in magnetic flux through the surface on the same circumference current is induced, so that is related. The circumference and the surface is related, because whenever we say flux, we associate a surface. Okay, whenever we say flux, we associate a surface. Without associating surface, there is no flux. Now, if you see here, I'll just make it a bit more clear. If you see here, come on, okay. Uh, Now current, for example, let's say current is produced here. Current is produced in this loop, in this red loop. Okay, current is produced. Now, let's say why there is current, because there is electric field. So there is electric field, E field. Okay, E field, there is E field, so there is E field everywhere in this loop, isn't it? That is why current is flowing. Yes or no? Yes or no? Yes, isn't it? Because there is electric field, there is that is why current is flowing. Because there is electric field, that is why current is flowing. Please see it very carefully. Because there is electric field, there is current flowing. Okay, electric field is there, just I made with this arrow. Okay, this electric field, this electric field, tiny electric field on that instance. Okay, and let's say let's assume, I'll assume with black. Let's assume let's take a small teeny weeny little area, and let's say DL. Okay, DL. Okay, DL. Now if you actually see it, what you'll find is, if you integrate the closed loop, if you add the electric field, what I'm trying to make you understand is, if you add if you just multiply integrate electric e field, all right, and over the over the over the teeny weeny little surface dl, okay, if you just multiply it, e dot dl, if you just multiply it and over the surface, for example, let's say here is dl and here is e, so I created a e dot dl for an instant, and if I add over the loop if I add over the loop if I add over the loop closed if I add over the loop, this is closed loop cl, so I'll just write cl closed loop. Then what you will understand is, you will get a emf, you will get a current that is flowing. Okay, this is again another important concept that Faraday has told. Okay, please see this, this is very important. If you understand this, that's it. Please see it, please see it, please see it. Okay, you must be able to see it, please see it. So if you add the electric field and the length, okay, if you integrate the electric field over the length, over the loop, you will get a current, because that's what Faraday has told. Faraday told this. Okay, this is what happens actually. Mathematically, it is correct. So this is what happens. Now what you will realize it is, the surface and the loop that is closing it, the loop is connected. Now the actual Faraday law of electromagnetic induction comes this way. So actual law of Faraday is, I will make it in detail. So actual law of Faraday is D minus, and so we have phi, right? D phi dt. So what is phi? What is phi? Open surface integral of b dot da, isn't it? Okay. So we have D. I'll just use black here. Open surface integral of b dot da, b dot da. Okay, open surface integral of b dot da. So this is d over dt. Okay, so ignore this minus sign, this is just there to compensate Lenz law. This is equal to closed loop integral of e dot da, dl, not da, e dot dl. Okay, now the condition is, this is essentially Faraday law of electromagnetic induction. This is what is Faraday's law, and this is one of the four equation of Maxwell. Okay, this is Faraday's law of electromagnetic induction. Now the condition is there. Condition is there. I'll explain condition. The condition is, here is the surface, here is the loop length. This length on which EMF is induced must be associated with the surface of this B dot dA. That means must be associated with this surface. That loop must be associated with the surface through which flux is changing. Only then it is valid. Okay? Only then it is valid. All right? So this is basically what Faraday's law of electromagnetic induction. And if you if you've understood till here, then you have done a great job. All right. If you have understood till here, you have done a great job. Now, let me see the timer. 4 minutes is left. Okay. So we have covered almost every important topics of electromagnetism, Faraday's law, Lenz law. Now there is one special topic. It is very very special that we will cover in the next lecture. That is a comparison in of Kirchhoff's law and Faraday's law. Okay, because it is the main law. It runs our economy. It is not the Kirchhoff's law. You will understand, and we will uh, differentiate between conservative and non-conservative field, and I'll show you one important experiment also. Okay, thank you. If you have any issues, please let me know through comment. Take care, have a good day, bye bye.